Well, here we are for Conversations with Colleagues again. This is something that has been going on for about 4 years now, right, Kim? And
Yes.
We've had quite a few presentations. Our speaker today has addressed you once before, but he's updating you today. Here's basically how we do it. Fourth Thursday of the month. There's some months we miss because, as Kim pointed out, the weather gets awfully nice in the summer, and it's hard to get people who want to listen to presentations, or give presentations then. But we'll be lining some more up shortly. Today's speaker is Guido Cervone, and he addressed you back in 2018, I think it was, on work that he was doing with remote sensing and so on. Guido, are you still an associate professor?
No, I'm a full professor now. I was promoted.
Well, I'm sorry, I should have updated this then. But you're still director of Geoinformatics and Earth Observation Lab, right?
Correct.
And also with the Center for Cyber Science and whatnot.
Yeah, it changed name now. It's Computational and Data Sciences, but same thing.
Right. So Guido's work spans the globe, and he's quite accomplished in the world of remote sensing and using that data for all sorts of purposes. And I can go on and on and on about the bullets here. His accolades are many. Some of the very interesting things are Guido has many hobbies, and one of his hobbies he extended into being an instructor for the U.S. Naval Academy sailing team. And so there's quite a few miles. Have you added to those miles over the last 5 years, Guido?
No, unfortunately, being in central Pennsylvania was not conducive to my offshore sailing.
Yeah, I get it. He came here from Italy at age 16. He has 2 kids. He has many, many hobbies like skiing, sailing, flying drones, which he's extended into his professional life. And Guido, this data is 3 years old. Have you bought a cell phone yet?
Yeah, I have a cell phone now.
Okay. I thought that was very interesting back in 2018. So
I haven't had it for 5 years. 5 years with a phone.
There you go. So without further ado, Guido, I'm going to let you carry on. I'm going to stop my share. I'll let you start share and fill the audience in as to how you'd like to handle questions and so on, okay?
Okay, so can you see my screen?
Not yet.
No.
Okay, so let me check why. Sorry about this.
Yeah, we were seeing it earlier, no problem.
Yeah, I might have done something. Just 1 second, share screen, and I'm going to go into my PowerPoint, and you should be seeing it now.
Yes.
Here we are.
Perfect, okay. And you do see the full screen view of my screen, correct?
Yes.
Yeah.
Okay, perfect. Right, thank you very much, John, for that introduction, and for inviting me the second time. I'm very happy to address this community. So today we're going to talk about atmospheric emissions and how they were affected by COVID. We are also in a celebratory mode. Our college, the College of Earth and Mineral Sciences, is celebrating 125th year today. And this presentation is also associated with a celebration for the college. So about questions, you can, in either one works. You can stop me during the presentation, or you can ask me at the end. Either one perfectly works for me, so whatever you prefer. I would suggest that if there is something that I'm not clear about, please do interrupt me, because otherwise you will not be able to follow the whatever comes next. Okay, so I will not be monitoring the chat, so I will ask probably John or someone else to to please monitoring the chat. So if there are questions in the chat, just please read them to me. All right, so little agenda for today. We're going to start talking about remote sensing, and I will give you a very personal introduction of at least how I got into remote sensing and why I think that is the coolest thing to study after material science, maybe I should say. Then we'll talk about human mobility in general and how COVID affected it. Very brief introduction about atmospheric emissions. And then we will try to answer two questions. The first one is whether or not COVID affected human mobility. And second, well, if that is true, what happened to the emissions? And I will show you some results from my own work about atmospheric emission trends during COVID, during and after COVID. Well, I should say COVID stay-at-home orders, because COVID, of course, is still going on. And then I will present just a few slides from that were published ever since. And then, very brief conclusions. So we'll start with remote sensing. And, to me, remote sensing was a journey. I am trained as a computer scientist, and I really discovered remote sensing towards the end of my PhD. So, but I consider it as a journey, and really the journey starts, at least for me, with Giovanni Cabot, or John Cabot, was the first European that led an expedition that, led an expedition that arrived in North America. It's celebrated in Canada, similarly to how we celebrate Columbus here in the US. And the first part of the voyage, he was working for the United Kingdom, and his first part of the voyage, he went all around here, North America, Terra Nova, but then unfortunately he died during the expedition, and the second part was led by his son, Sebastian Cabot. And he started in 1497, and the expedition lasted a little over a year. And the reason why this is important, because he comes from a city in Italy called Gaeta. There were many of the Europeans that were leading expedition to the New World, but actually Italians, Christopher Columbus working for Spain, John Cabot working for England, Amerigo Vespucci, I believe was either Spain or England, and Giovanni da Verrazzano, of course. So they were not working for Italy because, first of all, in the 1500s, Italy was not a unified state, was divided into many different city-states. And also there was not much interest into the New World because of the geographical location in the center of the Mediterranean. So John Cabot, he comes from this town, little town. This is a lowland. There is a big mountain over here. And then, this is the old historical medieval town. This is a map from 1700. And the reason why this is very relevant, because that's where I come from. My family settled in Gaeta in the early 1500s. So he left in the late 1400s. So it is not inconceivable that maybe some of my older relatives, I actually met John Cabot. And I've always been fascinated by him, having being from this town, almost, there is a big road right here, which is called Lungomare Caboto, and there are many monuments to him. So I grew up, with this image of Caboto. And this is an image of Gaeta. This is the mountain that I told you is right here on the lower left part of the image. This is the medieval town. And here on the right, it's me, 4 years old, sailing. This is a laser sailboat. This is my dad. And I really learn how to sail here in Gaeta. This is the view from my house. It's a panoramic view. So actually see this part right here continues here. So it's just highly distorted. But what I wanted to show you that I actually grew up looking at both sides of Gaeta. So you see, this is, basically the northern side and the more southern side. This is the big mountain. This medieval town is behind this mountain. You cannot see it from my house. And the reason why this is very important, because I always dreamt about circumnavigating it. So basically live here from this side and go around all the peninsula and make a landing on the other side. And I actually did that. This is me I think I was 11 or 12 years old. This is my aunt. And I didn't have a boat because my dad, I mean, I couldn't tell my dad what I wanted. I couldn't tell anyone what I wanted to do because they would have said no. So I actually built little sailboat rigging on my rubber boat because I always used to go start from here. This is the beach. And I knew that I could get in about an hour just to this point, and I knew I just couldn't use just rowing, all across, but I could do it with a little sailboat. So I convinced my aunt to come with me. We didn't want to do it alone. I told her that we were just going, like shortly after this point, and it took us 14 hours. So, it was a long journey. We started very early in the morning and we got here late in the afternoon. And for the whole time, she kept telling me, in Italian, per mare non ci sono taverne, which means at sea there are no taverns, because she had to eat and use the restroom. I didn't prepare for that. But eventually we made it. And the reason why this is relevant to this talk is that this is the actual map I used. As a kid, 11 years old, I did not really have access to maps or the internet. And this is what I found at home, which was a map from the 1800s. You see, Gaeta, all this part was not developed yet, but that's what I had to work with. And I discovered a lot of things in this journey because I had never seen this coastline. This was really new to me. And this is today. I just got this one a few days ago, and you can actually see my house. Actually, Google has a link for my house, and that's what I did. I started from Serapo, we went all around, and we got here in Lungomare Caboto. So you see, this is a remote sensing image. Google made it so easy for us to access it and to also plan. So I can imagine that, the new kids that want to do what I did so many years ago can actually plan, what to see. Maybe, there are some easier landings there are. I didn't know that there are. So, and this is fantastic. It's so easy, so accessible. And how did we get here? Well, this is a map of the world as was discovered to the Romans, so about 300 after Christ. So you can see it's quite detailed here in the Mediterranean, but as you move away from the Mediterranean, you get really unknown. Look at the England. This is Britannia Insula. So they, they knew that there was something there, but that was about it. And Africa, looks just like a triangle and so on. So this is in 300 years, and it took about 1,500 years to get to this. So this is one of the very first detailed maps that I could find, and it's almost perfect. The only things that are unknown, of course, the polar areas and Antarctica. Antarctica wasn't discovered yet in 1800. And this is a map from 1913. This is a map of my grandfather. So he was born in 1913. This is what was access to him when he started. And you see, it's actually quite detailed. So I actually really like this map because it shows the isochronic distances from London, and it's in the order of days. So this one is showing that, it would just take about, 5 to 10 days to get here to our areas from London. And the reason why I thought this was interesting is that, remember the book from Julius Verne, Around the World in 80 Days? Well, that was done just 40 years before this map was published. And if you start counting, yeah, it probably does take about, it is possible to go around the world in 80 days just by looking at this map. This is just pure curiosity. This is the world today with isochronic maps. The only thing I want to show you, you look at the scale. We went from from days into hours, and from London you can pretty much reach every part of the planet within 36 hours, except perhaps from some of those extreme polar regions, interior of Australia and Africa and so on. And this is, the Earth in 2021. I just captured this image a few days ago. And I want to show you that not only we can very accurately map the planet, but we can also map all phenomena that are occurring, like in this case, weather. And the reason why we can do that, so we went, in the last, just about, if you think about 200 years, from just a map to this is because of remote sensing. And so we have satellites, we have thousands of satellites that currently orbit our planet. And they gave us a bonanza of information. And in a certain sense, when you study Earth science, this is the most exciting time to be in the history of our civilization, because we have never known so much about the planet. We have never known so much, in part because of remote sensing. And there are two different types of orbits that I'd like to discuss. One is called geostationary orbit. They sit around 36,000 kilometers from the surface of the planet, and they can only be around the equator. And they're not stationary. They actually move very fast, but they look stationary from an Earth point of view. So that means that they rotate with a proportional speed of our planet, so that they always seem to hover 1 point over the equator. And those are the type that are used for communication, like satellite TV. You take your antenna, you point towards a location in the sky, you never have to change it because the satellite will always be in the same line of sight. And then we have the polar orbiting, which they orbit the planet from the North Pole to the South Pole as the planet spins underneath it. And the advantage of polar orbiting is that they're much closer, so a higher resolution, and they can see the entire planet with one satellite. Whereas in the geostationary orbit, we only have one constant view. So in order to create that image that I showed you before, we really need to have a constellation of them, which we do, and we're able to get this worldwide view of the planet and the weather. So if you think about what I just told you, that we were able to get from this unknown view of the planet in the 1800s, where we still didn't know that Antarctica existed, to nowadays, 200 years later, it's been remarkably fast. If you look at the history of the planet, and especially the universe, where we're talking about billions of years ago, about 14 billion years ago when the Big Bang started. And if you think that humans have inhabited this planet only for 250,000 years, 200 years that we went from knowing so much about the planet to just knowing, being able to map most of it, it is remarkable. There are a couple of images that I wanted to show you. This is called Blue Marble. This was taken by Apollo 17, the last mission to the moon in December 1972. And it's a very unique image because, as I told you, we are able to see the disk, so the entire planet, from geostationary satellite, but they are over the equator. Whereas in this image was taken where the spacecraft was not over the equator, was actually, this was the sun point. You can actually see Antarctica. This is unique. It's the only image that we have of this kind. And because, no new interplanetary mission, or at least manned interplanetary mission are planned. They are at the developing stage, but not planned. So this will be pretty much unique for the time being. And then finally, I want to show you another image that it still gives me goosebumps every time I see it. This was taken in February 1990 from Voyager. And this is where Voyager 1 was roughly here, so, past the orbit of Neptune. And, there are not too many interesting things to map. Once, Voyager went so far into the outer layer of the solar system. So they decided to turn off the imaging camera just because there were no data to collect. But just before doing that, they turned the spacecraft around and they took a picture towards the inner part of the solar system. And what you see right here, what is called the pale blue dot, it's our Earth, it's our planet. And if you think about it, that everything about our civilization is just in this small little dot, is, at least to me, absolutely astonishing. And again, this was collected in February 1990. And when I was doing this presentation, it occurred to me how most of those images that I showed you today were actually collected in December or January or February of different years. So most remote sensing big observations happen in winter. Just a coincidence, but it just occurred to me. Those are the current NASA missions. Those are missions to the planet Earth. There are also a few missions to the moon and to Mars. There is an entire new slide that NASA has, for the different parts of the solar system. The reason why this is important because I'm going to present results from this satellite right here, Aura. And it was sent a few years ago in orbit just to study the atmosphere of our planet. And when we talk about remote sensing, we're really talking about electromagnetic spectrum. What we're doing is to measure either reflected or self-emitted radiation from our planet. And the electromagnetic spectrum ranges from gamma rays, so very high frequency, very low wavelengths, all the way into the cosmic ray, radio waves and cosmic rays. And the visible part of the spectrum is a relatively small part of the spectrum. It just occurred between 0.4 and about 0.8 microns. And this is what you see here in this curve is the amount of radiation that is received by the planet on top of the atmosphere. And this particular, this red line right here is what is received on the surface. So what the difference between the blue curve and the red curve is actually the atmosphere. It's what it is absorbed or reflected back into space by the atmosphere. Primarily are gases, water vapor, like clouds, carbon dioxide, and then, there are many others, like methane, for example, but they actually have a smaller contribution. And the only thing that is important here to notice about remote sensing is how, this beautiful correlation between the Earth and the Sun. Because if you look at this blue line, which is the Sun, you see that most of the energy, and that this energy keeps going down asymptotically, getting smaller. Most of the energy, it is right here in the visible part of the spectrum. And also, if you do the difference between those lines, the visible part of the spectrum is also the part of the radiation that the energy is most able to absorb. So there is this beautiful relation between, what the Sun gives and what the Earth absorbs. And, if this wasn't true, the life as we know it wouldn't be possible. Okay, so we'll talk a little bit about human mobility. So we cannot directly measure people's mobility, but we can take proxy measurements. And we have a tremendous amount of measurements, and they're growing at an increasing rate, which is good because it means people like me are needed. We can estimate mobility from many different data sets, like traffic, for example, or, just even economic transactions, or just different type, like credit cards, for example, use, or for cell phones. And cell phones are among the most used right now because even me, that for many years resisted to have a cell phone, now I have a cell phone. So it is possible to precisely geolocate people. There are privacy concerns, of course, associated with this. But generally, while we cannot get data about individual people, we can get data aggregated. So we know that in a certain areas, there are a certain number of cell phones. If we assume one person per cell phone, then we can actually assume how many people are in one location at a specific time. And there is a laboratory called the CART laboratories that they provide cell phone data, so mobility data based on cell phones free of charge. Anybody can download. And there are many studies that have been done with this data. I've also used them. And then, what happened is that COVID happens, global pandemic, the end of 2019, that drastically changed mobility. By March, it spread through Europe. Italy was the first hard-hit European country, but then very quickly it spread throughout the world. And depending on the country, very restrictive stay-at-home orders or suggestions, sometimes were not orders, but just suggestions, were implemented worldwide. So what we actually could see is that people had to stay at home. Those are the COVID cases in the US. They really start ramping up, here in April. They really peaked in earlier last year, and then they start decreasing, both because of measures that were taken and also because of the kick-in of the vaccines. That's why it's so important to be vaccinated. And there are spatial differences. So once we, and this is spatial differences in COVID cases. I took this data just 2 days ago when I was, 3 days ago when I was preparing this presentation. And you can see that there is, a global, a downward trend all over the United States. But, it's highly spatial. There are, some states, that are doing quite a bit better than others. So this is the COVID spread through Europe, very similar than the United States. This is, again, I took this image a few days ago, with Northern Europe doing quite a bit better than, here the southern part of Europe. But do keep in mind that population here is extremely sparse. Sweden is an interesting case. It's the only European country that did not implement any stay-at-home orders. Actually, they were basically, the government was saying that, the more people got sick, the more herd immunity would be reached. And as you can see, it was a failed experiment. Whereas most of Europe, it's in this downward trend. Sweden still has among, the highest contagious rate in Europe. Here is a very brief history of the stay-at-home orders implemented in the United States. California was the first. And then, it spread to New Jersey, was very badly hit, in New York, and then, Pennsylvania, and was right here, about a week later. But then, we can say that, most of the states of the Union, they implemented some stay-at-home orders that were less restrictive than what we've seen in Europe, but they were orders. So effectively, the entire country kind of shut down. And do we see this in the mobility? Yes, this is the CART lab data. This is for New York, different counties of New York. And you can see that here, just, about the time that the stay-at-home order was implemented, then, it really went down. And I know this very well because on March 6th, I was supposed to go to Europe, flying from New Jersey, Newark Airport. I was at the airport when I decided not to go because the situation in Italy was so bad. Things in the US were still okay, but I was afraid just to go to Italy and be stuck in Italy. So, and it was a good choice because, as you can see, just a few days later, then, the virus had spread to the US and stay-at-home order were implemented in the US. So some observations. I created a video from this. I don't think there is time to show it. I need to actually start talking a little faster. But what I want you to know that there is a dramatic shift in movement since March 2019 in the United States. It's extremely regional. So we do not see trends, the same trends all over the US. In some parts of the country, actually the trends seem to have not slowed down or actually even increased. But, we see this generally in very sparsely populated area. All the highly populated areas, we see this mobility decrease. So is this only in the US? No, we actually see the same kind of patterns in Europe. As I said, Italy was the first country that was hit. So you can see the movement, percentage of business as usual was already reduced in the beginning of March, but very rapidly the rest of the cities in Europe, they have seen the same trend. And this will have long-term effect. This is data from airplane travel from the IATA. And this blue line was the trend before COVID. So you see there is an increase in flying trend, throughout the years. Then COVID happened, drastically decreased. And there is a trend, this is projected into the future. It will take several years before, using COVID baseline or, COVID setback scenario, in case, we don't recover as rapidly. But it will take several years for the airline industry to, to go back to the pre-COVID cases. And we see that already. There was an article on CNN yesterday about the price of air travel, how price is becoming it is actually more expensive than pre-COVID. And that is because of this. So atmospheric emissions, we have two types of emissions, natural emissions and anthropogenic emissions. They come from different sources. I actually have a figure. I will just show you here in the figures. And it is undeniable that anthropogenic, so humans, have changed the source of emission. So before, so a pre-industrial scenarios, without much of transport and industrial emissions, we have a certain atmospheric characteristics. And once we have transport, especially transportation, but also industrial emissions, then we see that there is a very different energy budget that is happening in our planet. So it is conceivable that if human mobility drastically reduces, then those new post-industrial emissions will change the atmosphere. And this is particular for a work in China, but I just want to show you those right graphs. Among the different emissions, I really want to focus on NOx's. And as you can see, for the most part, NOx's come from transportation. And PM2.5 and PM2.5, this is in China, so there is a lot of fugitive dust. Here in the US, most of the PM2.5 are from industrial and some residential heating, and a little bit of transportation. So, PM2.5, that's what gives asthma. They're particulate matters, and they come primarily from large engines, like diesel engines. Whereas NOx are primarily associated with small vehicles, like gasoline-based engines. And this is the hypothesis. Because NOx is more dependent with vehicular transportation, then we should see a decrease. Whereas PM2.5, that is more dependent with industrial operation, large diesel engines that, they were not as affected by the stay-at-home order, we shouldn't see a decrease. So this is our hypothesis. The data should show a decrease in NOx, but not a significant decrease in PM2.5. And let's see whether it is true. So this is the recent article that I published with my colleagues from University of Delaware. And we use data from 2015 to 2020. We look at mobility data from the CART laboratories, and we use PM2.5 and NOx data from satellite and also from ground sensors. And it is important because, the satellites, it will tell us the value integrated over the column. So from the surface of the Earth all the way to the satellite. Whereas, ground measurements, they really reflect the atmosphere at the ground where the measurements are made. So whereas satellite data, they're fantastic because they give us all this spatial data. They do not actually pinpoint what is happening close to the surface, where humans live. And we really need to study that part in order to understand reduction of the atmosphere because, the emissions happen at the surface. So this is our study area. It's the continental United States. Here I have a map with populations. This is in logarithmic scale. So we're talking about, when we are 6, we have about 1 million. Here we have about 10 millions. So not surprisingly, Los Angeles area is the most populated county here in the US. And we have, quite a lot of population here in the Northeast. And as we all know, the central part of the United States is more sparsely populated. So this is really good, but we also need to have this map. This is urban versus rural areas. This is actually, I created this map just by looking at light from satellites. We look at the planet at night, and then we see the amount of lights. The reason why this is important, because when we want to look at a resolution that is smaller than counties, what we have here, as you can see, it looks like, there are like millions of people living in this area, whereas in reality, that's a piece of desert. It just encompasses the county where there are many people. So just keep in mind that even though a lot of the graphs I'm presenting you are at the county base, that's because that's the mobility that we have. I will show you some results that are really down, looking at the individual rural versus urban pixels. These are the data that are available. The blue dots are the PM2.5 stations, so we have quite a few. The green are the NO2 stations. We do have, but quite a bit less, unfortunately. Oh, sorry, that's my bad. Quite a bit less. And when I mean no data, this is data for which where satellite data are missing for a variety of reasons. So, So unfortunately, sparsely populated area of the US, we actually do not really have good NO2 estimation from satellites, but we can concentrate on the west and the eastern coast all the way to the divide. So this is the mobility. This is March 1st to June 1st, 2020. We've done this study in June, so no data that I will present to you is past June. And this is a mobility as a percentage of what happened in the previous 5 years, 2015 to 2019. So everything that is blue, it means that there is a reduction in the mobility. Everything that is in red, there is an increase in the mobility. So what do we see here? That here, especially in the Northeast, New York, New Jersey area, we have a drastic decrease in the mobility. And by the way to read this graph, 100% it means that there is business as usual, there is no change. So everything that is in white here is about no change. If it goes to 0, it means that we detect no mobility. And you see here in New York, so basically people stay at home. And this means that there's only 30% mobility that we had before. And here it means that people are moving 1.5 times more than before. There are a few counties, as I said, very sparsely populated county. Maybe the only exception is here, this county in West Virginia. But for the most part, we can assume that the entire US kind of stopped. And it did so very drastically, like within a period of 2 weeks. And we see this trend in the data. This is the Descartes Labs. Before I showed you the data only for New York, this is the data that I compiled for all the locations for which we have ground measurements. And you see that there is a drastic decrease. You know, in the second week of March, it really went down and it stayed down. It started recovering only, you know, towards the end of May. It's very cyclical. Those are gray areas, those are the weekends. I just mapped them for you. And not surprisingly, you know, people tend to stay, you know, to move less during weekends. There's not a commute or a short, there's usually not a commute during the weekends. But during the week, we do see movement, and, you know, it's actually quite, you know, in some places quite high. Remember, 100% means business as usual, 0% means no movement at all. And it's very spatial. So this is PM 2.5. So we're looking at the emissions. So everything that is in the yellowish means that, you know, it's similar to what was before. Everything that is green and blue means a drastic decrease, and the orange means that it's increased. So it does look that these areas of the US are seeing a decrease, some, and also here on the west coast of the United States. That's PM 2.5, sorry, I wanted to show again. But you know, it's nothing very significant, right? You know, you can see here a little bit of green, but for the most part, you know, we are in this part where there is, you know, maybe a little bit decrease, a little increase. But here with NOx, it's a completely different picture. Aside from a few red areas that we see here in the sparsely populated area, we're here in Texas, most of them are in the green, in the blues, sorry. So there is a drastic decrease. This is in parts per millions in the NOx. And this is the picture that the satellite gives. Always for NOx, same period of time. The unit is different because the satellite measure in a different unit, but we can really see the spatial distribution here. Look at New York and New Jersey, drastic decrease here in the NA area. And, you know, overall, most of the Northeast. There is a little bit of funky things that happen here in Pennsylvania and here in New York, but for the most part, we do see a decrease nationwide. This is just a zoomed area of NOx. And what is most important is right here, you know, is the New York, New Jersey area. And those are some, you know, the graphs. I'm going to spend a little bit of time here explaining to you what it means. Here is the NO2 for every pixel of the United States taken from the satellite. So this is every single pixel in the satellite view, comparing the baseline 2015 to 2019 here on the horizontal axis with 2020 here on the vertical axis. And everything that is in red, it means it's statistically significant. It's a statistically significant reduction. Everything that is in blue is a statistically significant increase. And you will see that, the red dots are a lot bigger than the blue dots. So there are many more locations in the US where we have statistically significant reduction than areas where we have statistically significant increase. So that what this picture tells us is that NO2 overall has decreased. But remember, this is the satellite. So this is telling us what is happening in the column of the atmosphere. So it is a little bit hard to say with any certainty whether this is directly related to the human mobility, because we're measuring over the entire column. So this reduction might be due to NOx being transported from faraway areas. So what we have here, though, here on the right side, sorry, I'm going to jump a little bit. So I describe here top left, I'm going to describe here top right. We see the aeronet, so those are the location on the ground, the location that we have available. So those are really related to the human mobility because those are measurements taken at the ground, at the surface, where emissions are happening. This is not NO2 that can be transported from faraway field, or very much less so. And again, when we compare the baseline to 2020, the statistically significant, almost all of them. We have very, very few stations where we see an increase. Remember, there were sparsely populated area out west. And then, we have a few that, there is no statistically significant changes. And this is very important because, it's a good evidence. It's not a proof, but it's a good evidence that mobility did affect the emissions. Then what I did, I took the satellite data for the very same locations just to make sure that there is a high correlation between satellites and ground emissions. And there are many less points because remember, there was a lot of missing data in the satellite. So unfortunately, the number of points are less. However, the trend is the same. And then what we did, we have taken those satellite measurements for the whole US. Now that we know that, we can probably trust those measurements, I divided into urban pixels and rural pixels, not according to the population, but according to light detected from satellites. So it's a much finer resolution than individual counties. And they tell us, quite an interesting story. In the urban areas, we see the general trend of reduction, whereas in the rural areas, we don't see that. So this is suggesting that human mobility is more affecting urban areas than rural areas that we have seen in the graph, and that it is resulting in different emission scenarios. And then here we have, PM 2.5 from the ground, and it is showing actually that, there is some decrease, but there are also some increases. So there is not a clear trend. And this is very important. Fortunately, I don't have PM 2.5 data from satellites, so we only have to rely on the ground emissions. But this is supporting our hypothesis. Remember, NOx, based on small vehicular transportation, we hypothesized that it was more affected than PM 2.5, which is, from industrial activities and big diesel transport, trucks, locomotives, and so on, trains. Because the stay-at-home orders that did affect individual people, therefore driving would be affected, but they did not affect as much big industrial productivity. So this is quite important because it is supporting our initial hypothesis. So what have we learned? Well, NOx shows a stronger decrease in 2020 compared to the baseline that we computed for the previous 5 years, but PM 2.5 does not show the significant patterns. Most changes are seen in the northeast of the United States, also California should add. However, this study was performed only up to June in 2020 for the United States. However, I will take the next 2-3 minutes to show you that this seems to hold true worldwide. So those are NOx emissions in China. Those are from a European satellite called Sentinel-5P. This is a preliminary emission. I took this directly from the ESA, the European Space Agency website, and it is showing February 2019, so business as usual, February 2020, drastic decrease, and February 2021 is actually higher than 2019. And this is a very interesting graph because you see my first bullet, this can actually be used to estimate industrial output of a country, industrial output and movements and so on. So we can assume that China went back to its pre-COVID production level, and this is actually supported by economic data. Those are always NOx emission in China. This is I took it from this recent publication. They actually it's an interesting article. They use different satellites, they use different models, and they're actually showing 2020 back to 2000 to the baseline 2005 2019, and this is is rebounding. So it doesn't show as new data as what I showed you before. But what is important is this bullet point that I got from them, that NOx emissions were reduced by 36% from early January to mid-February, with more than 80% of the reduction occurring after the lockdowns of the provinces. So again, very strong evidence that human mobility is directly affected to emissions, NOx emissions. This is PM 2.5 over India. And we see some reduction, especially here in the Indo-Gangetic Basin, before and after lockdown. So here in India, it seems that there is a correlation between from PM 2.5 and COVID. Those are NOx emissions all across Europe. This is business as usual. This is COVID-19. And let me show, it's a video. So here we are in February, we're getting into March, and this is, where Italy shuts down. You see Italy and France, they really go down, Spain follows after, and then, there is, this little bit of blinking in Germany, because whereas those were prolonged, lockdown in Germany was more periodic. And then you can see here, no reduction in Sweden, as we said. Those lines here, those are shipping lanes. There's a lot of cargoes. And we can summarize this in those graphs. This is from Italy, March 2019 to 15 March 2020. So pre-COVID, and you see Italy has not recovered yet. We've seen with China, we go back to the pre-COVID emissions. Italy not so yet, and the very same thing for France. Remember that Italy and France were very drastically affected by COVID, and in Italy, especially this area right here, which is the industrial productivity of the country. So, some conclusions. Atmospheric emissions are intimately associated with human movement, and I hope that I convinced you. COVID presented a unique opportunity to really slow down human movement, to really see what happens to human movements to the emissions as we drastically slow down this movement. Decreasing mobility affected emissions. We've seen that in the United States, NOx associated with vehicular traffic was most reduced, whereas PM 2.5 was less affected. It's very hard, at least to make very strong conclusions based on the data we have seen. But this seems to be true also for other parts of the world where emissions were drastically reduced during this terrible year of pandemic. Emissions seem to be returning to pre-COVID level in most places. Even Italy and France are slowly catching up. What we don't know is there are some longer term effects that we're going to see with this drastic emission reduction and drastic reintroduction of the emissions. And with this, I'm right at 45 minutes, so I will conclude my talk and I will take any questions.
Well, thank you, Guido. That was fascinating. I have a couple of questions. May I start?
Please.
All right. So with more people staying at home during lockdown, they're not driving their cars as much, but their heating and cooling energy consumption presumably went up significantly with many of them being at home. Do you have a database or databases that are accessible to try to track that?
Yeah, John. So we try to look at PGM data exactly related to that. So there are two, two flips of the coin, I think we say. Yeah, you're absolutely right. So traffic goes down, so NOx goes down. PM 2.5, which is associated with the heating and cooling, especially like diesel heating of homes, then, this should go up. But remember that, that is offset by most commercial activities really taking down their heat. I don't know if you have been on campus during the winter. I mean, my office was freezing, and right now there are probably 90 degrees in my office.
That's a good point.
So those have been offset, but perhaps not quite as much, because it is a matter of efficiency. It is much more efficient to heating and cooling commercial space than it is on residential space. So we should see an increase in basic electricity usage and like diesel use for the heating, but it is offset. So the delta is not as large.
No.
So, and I think that's why those PM 2.5 data that I showed you, that there is some increase, in some other parts are decreasing, but it's quite a bit difficult to actually narrow it down to what is happening.
Were there any measurable changes in methane emission, primarily from our shale gas production and so on?
Yeah, I actually don't know. I didn't look at that, so I cannot answer the question right now.
Okay. There's been a question up on the chat for a little while.
Oh, yes.
Right, and it is, are the emissions estimated from models based on other inputs or from measurements in the atmosphere?
So yeah, this is actually complicated. It depends a little bit on the model. So usually the way the models work, there is first a data simulation phase in which observations, they're input into the model, but they're not directly inputted. They are statistically corrected. Think a little bit of the model as a human body, right? You cannot just take the heart from a person and put it into another person. There'll be a rejection. So there must be a compatibility before such a transplant is made. Well, very similarly, for an atmospheric model, we cannot just input the data. We have to make sure that they're consistent with everything else. So real observations are taken into the model. They're statistically corrected. Then, the model runs, and then, we compare the results with other observations. If it is done retroactive, if it is a prediction for the future, we would have to wait to do that. Satellite measurements, they play a fundamental role into this, but they are not directly assimilated into the model. There is also one very important aspect of model, and this is something that I'm doing right now, is that, well, I kind of told you that there is enough evidence in order to believe that this reduction in vehicular traffic affected emissions, but I haven't really proved it. So what the type of research I'm doing right now is that I have traffic data that's actually not very difficult to get from the DOT, and I'm talking about highway data. And then I'm using those as sources for the model to estimate emissions. And then I'll come up, with many different cases. And so in one simulations, we have, traffic from last year, and we would simulate the emissions. And then, we have the reduced traffic, and we simulate emissions. And then, we can do some drastic cases in between. And then compare the model results with the data that I just showed you. If we can prove that we simulate less traffic, and therefore we simulate less NOx emissions, and that simulation shows consistent reduction with what we see from the satellite, then we would know that yes, there is a directly, or we have even further evidence to show that there is a direct correlation between the mobility, reduced traffic, and the NOx emissions.
Some more questions from the audience?
None in the community room, John.
None in the community room. Okay. I have another one.
Please, John.
So as worldwide productivity changed during lockdown, you were able to see differences in NOx production and so on. Were you able to detect anything with regard to productivity in the timbering industry? where lumber prices are up on the order of 4 to almost 5-fold since that time last, when COVID started.
Yeah, that's a very good point. And in fact, one of the projects I wanted to do this summer was to build a little deck, and I gave up on that. I'm just waiting for hopefully the prices to go down. So that's a quite interesting question. So, I mean, I did not study that, but I've been thinking about using remote sensing observations as proxy measurements for productivity. And I was just talking 2 days ago to MGA, the National Geospatial Intelligence Agency, if I can get a little bit of funds in order to do that. Basically, to try to come up with like a prediction, like a weekly prediction of what the industrial productivity of entire regions are based on their emissions. Because now we know what was, like a full, like before COVID, and then, we know slow down. So the delta is basically, it's, industrial productivity that is resuming. Now, for the logging industry, for the timber industry, what I think would be very interesting to look is probably, yes, at the transportation emissions. So, you need to transport those logs and process them. So I think in theory, it should be possible to do that. Now, my understanding is that, the reason why the price of timber is so high right now is a combination of facts. One, all the flooding destruction in the southern part of the US, which meant, that there is higher demand, higher than usual demand because, the reconstruction needs. At the same time, we have less imports from Canada. And that was, to me, was fascinating because I know that, basically the US-Canadian border is closed, but it's only closed, to people, not to goods. So the question is, how come a border that is not close to goods actually means that there is less traffic of goods that we need? And the way that it was explained to me is that, well, goods, they don't just travel, without any plans. And that industry wasn't probably as fast as we have been, to use Zooms and, like basically telecommuting. So in other words, the lack of movement across the border did influence, or even, the movement of commercial goods, even those were not restricted. Now, this is not my expertise. This is what it was explained to me. It makes sense. I'm not entirely sure if it is true or not. But what I was told as well by colleagues in the forestry is that the price of wood should go down. That, as, the border gets reopened between Canada and the US, which hopefully is going to happen very soon, then, the flow of goods will increase, and then, the extra demand, will be met. So the price of wood should, timber should actually resume to pre-COVID levels soon.
Okay.
Yeah.
Thank you. Any other questions from the audience?
None here, John.
Okay. Well, Guido, I think, there's a question from John.
There is one question, John. Yes.
Joan, you're on mute.
Yeah. You're muted.
Okay, I've got it. Sorry, it took me a while to get myself unmuted. Is it possible to take these data and project them forward with regard to an expected adoption rate for electric vehicles, including cars and, ordinary trucks, because I gather that really heavy duty trucks are sort of in a different category. But is doing something like that possible? And would it be useful to do it if we knew and we're trying to decide whether to buy an electric car or electric, a little truck, panel truck, whatever, pickup? would that be something that would be useful for people who are trying to decide whether it was important to buy an electric vehicle?
Yeah, thank you for the question. So yeah, it's deeply doable. And in fact, this has been done, is continuously being done. And there are two main ways of doing it. One is very simple, purely statistics. So you just look at the volume of cars, and then you know how much a car is polluting, and then you can come up with curves that tell you what is the emission. Unfortunately, no, this is simplistic. It works, but it doesn't tell you about the effects. Because the truth is that whether I think we could agree that pollution is bad, it is also true that it doesn't affect the planet in the same way. There are certain areas where pollution can be absorbed by the planet in a shorter time, whereas there are other areas where pollution actually just lingers around, and that is because of atmospheric circulation. So the best way to do it is actually to run a numerical model, atmospheric numerical models, where there are different emission scenarios, just like what I mentioned that I would like to do right now. I take traffic and know where the roads are, and then I simulate what kind of emissions we have. Now, if we start working with electric cars, of course, that the amount of NOx will actually go down, and you can simulate it. Everything is good. Not quite. There are quite a few studies in China where they've shown, both with observed data and more forecast data for the future, where they're showing that the adoption of electric cars is actually increasing pollution. Mm-hmm. And the question is, where does this electricity come from? So if the electricity is generated using coal, right, and think about you're replacing a rather efficient engine that generates very little PM2.5, some NOx, but that can be reduced, with very highly polluting coal power plants. So on one hand, yes, we can simulate it, but then we also have to simulate how that electricity is being produced. And this is what makes it very, very difficult. And this is why, things like the Paris Accord, that fortunately, we have rejoined. I'm a big fan of the Paris Accord. They're so important because, we're not regulating individual industry. We really come up, with global projection, and then each country has to implement how that particular reduction is being made. So it's a very complicated problem with atmospheric pollution. And there is an example that I give to my students. It makes them laugh a lot, but to understand what it is that I think that pollution, atmospheric pollution, is a little bit, like peeing in a swimming pool and having two areas, one where people can pee and one where people cannot pee. It just doesn't work that way. This is really a global problem, and it cannot be solved unless, all countries, they work together. That's why international agreements are so important.
Okay, too many variables at work, because we don't know at what rate electricity is going to change, and the way that it is produced is going to change. And in some places like China, it's going to go in the opposite direction of the way we hope. Thank you very much. That was a very clear answer.
Yeah, and I will just say a couple of things about electricity production in China. It is actually going in the right direction there too, because of their reliance on hydroelectric and also nuclear. So they are phasing out the coal, and they are. It's one of the few places in the world where there are new nuclear power plants, being, coming into place. I truly believe in nuclear power. I wish, we had more nuclear power. But so China, they are reducing their carbon-based emissions, at least coal-based. India is not. So India is a problem right now.
Thank you once again.
Yeah.
This was an amazing presentation.
Thank you. Thank you very much.
Thanks for doing this for us.
Yeah, I think time is up.
Guido, I have one more question. So as we locked down and stayed home, other segments of our industries, like deliveries, from Amazon and Instacart and takeout foods and so on increased dramatically.
Mhm.
Is that data available, and is it granular enough to give you useful information?
So we had some data available. Honestly, we did look at it, some estimations. Now, keep in mind though that, okay, food delivery, yes, it's regular cars, but like Amazon, UPS, they use trucks.
Right.
Trucks, they're diesels. So, we wouldn't see NOx reductions because, diesel pollutes soot, PM 2.5. So that is one of the reasons why I think, the PM 2.5, we have some decrease, some increase. Is very hard to make consistent predictions. But we do have data for that. I mean, remember, proxy data, but we do have estimation. And when we are, especially for the DOT, when we have traffic data, we do know how many passenger vehicles, how many trucks went through the, the different highway, the toll boats. So we can simulate that.
Right. Is Easy Pass data available to you?
Aggregate data, yes. So in other words, I know how many cars per hour they pass a specific route. That I do have it.
Gotcha. Well, thank you. This is a fascinating topic. You did a great job.
Thank you.
I'll ask one more time. Are there any other questions? And if you want to review the presentation again, it will be on the website for the 125th celebration of the College of Earth and Mineral Sciences. We're moving forward with all the lectures being recorded in that fashion and put up on there for perpetuity. So Guido, we're going to compare in 5 years.
It's still true.
And I'd like to say one more thing, and that is the Earth and Mineral Science went out there, students and faculty, and planted a lot of trees in the celebration of their 125th anniversary of the department's founding. And I just sent around some information about that to people that I knew to give the Department of Earth and Mineral Science some well-deserved publicity, because none of the other departments were doing that, this past spring. And I just thought that was great.
Well, thank you.
Thank you. Goodbye.
Okay,
Thank
so
you.
we'll see you. I'll be announcing the next presentation sometime in the near future, but we do not have one scheduled for June at this point. Okay, so thank you, Guido. That was excellent.
Bye.
Bye.
Take care.